average slope idea. I like this average slope idea.
Are we still trying to get it?
Oh, we sure are. That's the whole point. We're trying to get a model for prediction. So this is fantastic. I just got a third. Trey, you said 48 million. Chelsea said 55 million. And Frank is saying 66. Now that's a pretty wide range of values, isn't it? From 48 to 66 million. And you only have 300 million Americans. And under age 65, I'm guessing is probably maybe 200 million of those, maybe even less.
That's what we're using.
Hang tight. And here's the deal. Here's the deal. I love what you're saying, Frank. I love what you're all saying. The idea is, which model, which equation should we even use? We're hammering away at it right here. Whatever equation it's going to be a line. A line has to have two things. What are those two things? Well, 2 points. But I hate that point slope form that they make you guys learn in algebra class. I personally like the form, and I don't know, if you disagree with me, you can totally use whatever form you want. I like it when it's y equals mx plus b. That's more user-friendly, I found, in history than any other form. I mean, there's other forms like point slope, and there's other things like what's the other one? That's slope intercept, there's point slope. There's standard form. They're all fine. There's nothing wrong with any of them. The reason I like this one the best is because it puts the dependent variable by itself on one side. And I love that, because all you got to do is put an input in here, apply a function to it, and out pops the dependent variable. It's the only one of the three forms that does that. That's why I like it. Plus, handily enough, any technology you use also uses this form, I think for the same reason. So what we've got to do is we've got to find slope, and we've got to find this y-intercept. That is our job for this model, is to find that slope and intercept. And I think you guys are already on the right track, because you are having me do this average slope, which essentially is going to hone in on where how tilted the line should be. I don't think, for example, we should tilt it at a slope of 3 over 2. Because if it's tilted at 3 over 2, I think it's too tilty. It might be too tilty to stand for anything else. For example, suppose we said, you know what's going to be a great line? This line right here, through that point and that point. I think that's going to overestimate later on in time. Okay, then you say, okay, to hell with that. Let's use that point and that point. Well,
it should be 2.5 every 2 years.
Is that what we got for an average? Let's do it real quick.
That's the average.
Let's take the average of them. We got 1.5 here, right? 1.5. 3 over 2 is 1.5. This slope is 1/2 plus 0.5. Plus this is 1. You guys see what I'm doing here? Yeah. And this is 1.5 again. So each one of those slopes is paired. Each one of those slopes is paired with one of these stair steps. This one here. This one's paired with that one, and this one's paired with that one. Cool, cool, cool.
Oh, I just took the 3, 1, 2.
Hey, that's okay. I'm going to use all 4 to be thorough. Then we're going to divide that by 4.
Yeah.
Which are our first average of the class. Get used to that. We're going to do it all the time. We like taking averages. They're very, very handy. They're very, very useful in the world. So what do we get? 1.5, 2, 3, 4.5 over 4. That's 9. 45, 40 is 9. Is that 1.125? Check my math on that one. 1.125, 1 and 1/8. Decent, decent. Okay. That's nice. That's a nice average. That's a nice average, right? 1.13, depending on how precise you want to be. Right? So the question is now, we now have an average slope, yeah? We've now got an average slope, we understand. Is anybody bothered by the fact that we only used sequential slopes like this? Like we didn't use, for example, the jump from 92 to 96, which would have been 4 over 4, which is actually a 1. Anybody bothered by that? You don't have to be. I'm not trying to make you bothered. We okay with that so far?
Would it make a difference?
It would, depending on how you group them. It could make them different. The overall change, there's one thing that will be the same. If you start at the beginning and end at the end, what is that? That's 3, 2, 1, and 3. That's 9 over 8, which actually ends up being this guy right here. But it depends. As long as you break them up consistently, it won't change a damn thing. But depending on how you break them up, if you're not consistent about it, you can get different slopes. But as long as you're consistently breaking them up, it won't change a thing. Fair so far? Okay, that would be the average grade versus the instantaneous grade. We'll get more of that in this class too. Perfect! We got ourselves a slope. So if you look at our model, y equals mx plus b, m is now 1.125. Yay! What should the y-intercept be? Because we have to pick that too. We now know how tilty the line is, right? So we now know the tilt of the line on average is between these 2 points right here. That's the tilt. Now the question is, where should it, how up or down should it be? And that is a question here, right? Now we figure out where to do it. Now, is anybody growing tired of this? Is this wearing you out a little bit? I want to give you 2 things to think about. First of all, suppose this data set had more than 5 data points in it. Suppose the data set had 100 data points in it. How many slopes would you have to then calculate?
Just use the
99. Well, right, but that's assuming that's even correct, which raises my second point, Tom. My second point is what we're doing even right? Jeremiah?
You can't do the same thing like we did on Monday with the stairs, the randomization.
Absolutely, totally, friend, totally. But here's one concern, and you guys aren't even thinking about this yet, and you shouldn't be thinking about this yet. You're assuming that whatever the line we're using is going to go through at least a few of those points. I got news. There is that is actually the best fit line for the data. That's the best possible. Could you kill, Tony, the other lights if you don't mind? Because some of this is red. That's actually the best fitting line for the data. Remember our slope of 1.125? That's pretty close to the 1.05 that the best fit is. It's not perfect, but it's close. The actual best fit is 1.05. That's the slope, 1.05. Plus, the y-intercept is now 33.1. 33.1 is the y-intercept. And if you trace it back, you can kind of see that it would eventually. Now, is anybody concerned with where that line sits with the data points? Is anybody concerned? Tell me if you are. Is anybody nervous that it's not doing what? It's not actually passing through any of the points. How the hell can that be the best fit line if it's not passing through any of the points? How can that be? Average what? I love that, Frankie. Go.
It's because it's the average slope versus the...
It's a different kind of average. Oh, Frankie's saying it's a different kind of average. It's another average, but it's a different kind of average. Chelsea, what's on your mind over there?
Nothing.
Nothing? Are you sure?
I'm sure.
Is it the angle?
The angle is tied to the x's and the y's, for sure, absolutely. But the question is, what's the optimal angle? See, there's lots of different angles. We can rotate this line a bunch of different ways. How do we know to stop on this one? Now, I want to answer this in 2 ways. One is shorter than the other. I have a video that I've made to explain, we're about to explain to you now in 2 minutes. The video goes for about 7, and it's much more in detail. But I want to share it with you now as to why that line fits better than any other line, okay? Okay. Erase a little bit. Okay, I'm going to erase all this beautiful work we just did. I apologize, it was wonderful, it really was. I am going to slap the old curve back on there, though. No, here she is. Okay. Now, let me start and stop the camera again.